Assalamualaikum, hi student. So today we will talk about refrigerator and heat pumps 6.4. We have covered 6.1, 6.2 and 6.3 before our break. So first let's go for refrigerators. So this is the schematic diagram of a refrigeration system. So first the process start with compressor, then followed by condenser, then you will go through the expansion valve, or we also call it throttling valve, okay, and then last process is evaporator. So basically if you can recall back when I introduce you to the second law of thermodynamics, remember that the second law of thermodynamics give you the direction of heat, okay, the direction. So here, so normally if you have a hot water in a cup, normally the water will spontaneously the temperature of the water will spontaneously reduce from high temperature to lower temperature on its own. So the reverse process cannot happen, okay, it cannot go from low temperature to higher temperature. So the process, okay, if you want to have this reverse process, you will require a special device called refrigerator. So for refrigerator, you will transfer heat from low temperature medium to high temperature medium. So refrigerator, also like a heat engine, as we have covered previously, is a cyclic device. So here you have first compressor, condenser, expansion valve and evaporator. And the working fluid that go through this cycle is refrigerant. Okay, so first your refrigerant vapor here, okay, here enters the compressor. Here you have refrigerant vapor, okay, enters the compressor, and you will require additional work. Usually it's electrical work, okay, to compress the refrigerant work so that your pressure will increase. So once your pressure increase, your temperature will also increase, and then you will enter the condenser. Here what happens is the vapor will flow through a coil inside the condenser, and during that process it will reject heat to the surrounding air, to the surrounding medium. So after that you will get a refrigerant liquid here after condenser. Okay, the pressure remain the same, but after you release your heat to the surrounding, so of course your temperature will reduce. So next you will go through throttling effect, so, where your pressure and temperature will drop drastically, okay, and then you will go to the last process, which is evaporation. So from liquid you will get your refrigerant vapor by absorbing heat from the refrigerant space. Okay, so basically that is the four main process for refrigerators. So it's for our household refrigerator, the freezer compartment is your evaporator, while your the coil at the back of your refrigerators is the serve as condenser. Okay, that's why you will normally see excess liquid near the coil. Okay. So now we normally measure the efficiency of a refrigerator by terms of coefficient of performance. So our objective for refrigerator is to remove heat from the refrigerant space. So QL is our desired output. So the equation here is COPR, refrigerator equal to refrigerant output divided by required output. So since our desired output is QL here desired output divided by W net in. Okay, so if you can recall back, W net in is equal to QH minus QL. So just replace this equation, bring this up. Okay, so you will get to this QL over QH minus QL. So it depends on your data. So you can either use any of these three equations. So can the value of COPR be greater than unity? The answer is yes, can. Remember that COPR, okay, this is not the same as efficiency of heat engine. So in our last topic, heat engine cannot be more than 1. But for COPR, it can be greater than unity. Unity is 1, okay. What happens is if your COPR greater than 1, that means the amount of heat removed from the refrigerant space is greater than your work input. Okay, QL is bigger than your W net in. So this is for the case where you have COPR greater than 1. Okay, let's try some example. So a household refrigerator with a COP of 1.2 removes heat from a refrigerant space at a rate of 60 kJ per minute. Determine electric power. Electric power is your W net, W in. Okay, consumed by the refrigerator. Okay, no spelling here. The B determine the rate of heat transfer to the kitchen air. So the part B is asking for your QH. Okay, kitchen air, QH. So first, let's start with the basic equation. So COPR is equal to QL over W net in. Okay, so the question asks for W net in. So you have to rearrange this equation. Is equal to QL over COPR. Okay, then QL is already given. Here 60 kilojoule per minute divided by 1.2. So your W net in is equal to 50 kilojoule per minute, or you can convert this to kilowatt. So just divide by change this unit because we want to have kilojoule per second. So you will get 0.833 kilowatt. Okay, this is the answer for part A. So for part B, we need to calculate the QH. So remember the relationship. W net in is equal to QH minus QL. So we want to calculate QH. Okay. So QH. So bring QL to this side. So W net plus QL. So our W net just now, since both the units are in minutes, so we keep using 50 kilojoule per minute plus 60 kilojoule. Okay, so now, so your QH is equal to 1110 kilojoule per minute. So this is the answer. Okay, it's not necessary. If the question does not ask you to convert, it's not necessary to convert. But yeah, you can leave it like this also. This is also correct. Okay, 6 kh. Okay, so I will continue heat pump in our next video.